I want to thank everybody for coming along this morning and for getting up so early. Must be tough to get up this early every morning when there's no office where people look over your shoulder to make sure you are. So thank you very much for making
the second meeting of the morning, actually, for some of us.
I do feel the pain. This is a talk that centers around what I've been up to for the last two and a half years, and it's fairly. I've tried to keep it high level, and so if things are unclear, it's probably my fault, and I would encourage you to just interject. And keep in mind that I'm German, so even if you're trying to be rude with your interjections, I probably won't even notice that you're trying to be rude. And somewhat pretentiously, I've titled this talk Optimization-centric Generalizations of Bayesian Inference, because that is essentially what I'm interested in. And yeah, we'll just go from here. So if I want you to talk anything away from today, even if you decide that this is not really an interesting talk for what you're working on, or it's very unrelated to anything you're doing, and you leave halfway through, there's one thing I really want to ensure that you take away from today, which is that Bayesian inference is just an optimization problem. It's a single optimization problem. And actually, it's an optimization problem that when you solve it, you make relatively strict assumptions. And I also want you to take away that these assumptions you have to make, they're actually often violated in machine learning. And we'll see why that is later on. And you could be solving other problems instead. In fact, there's a huge class of problems you could be solving instead that are similar but different to the Bayesian inference problem. And I would argue that in machine learning, we would actually often do better to solve these other problems rather than the Bayesian inference problem. And that is basically the broad pitch of today's talk. The way that I want to convince you of this is in 3 steps. So first, we'll revisit the Reverend Bayes and his wisdom. So we'll look at Bayes' rule. We'll look at the assumptions that actually underlie Bayes' rule once you apply it to statistical inference. And then we will look how modern machine learning is actually often at odds with these assumptions. And then once we clarified that first step, we'll move on and we'll look at the optimization perspective on Bayesian inference. The key here is that you can rephrase the Bayesian posterior as the solution to a variational calculus problem. And then we'll look at that variational calculus problem and notice that it's actually quite modular and that different aspects of the problem exactly solve the different problems that you face when you do Bayesian inference in machine learning. And we call this generalization the rule of 3 because it consists in 3 arguments, and these 3 arguments solve the 3 problems that you have when you apply machine learning to when you apply Bayesian inference methods in machine learning. We'll go through some special cases of this generalization because it turns out it actually encompasses a lot of other things that are out there already that have been motivated from a somewhat different standpoint. And then we'll go through 2 simple, very brief applications of this in an inference context. So where we now take this mathematical object and actually apply it on 2 real-world data sets and see that it actually does what we expect it to do. And the third part is sort of a collection of sorts where the individual parts of the third part of the talk will be somewhat disconnected because they come from different papers and they look at different theoretical properties, I should say, of this rule of 3. Amongst which is that you can actually derive axiomatically that this rule of 3 is a problem you want to be solving. Another thing you can do with this rule of 3 is it actually allows you to reinterpret variational inference as a constrained version of the original Bayesian inference problem. And that yields a fairly straightforward optimality result, where optimality is defined in a narrow way here. And then we'll briefly talk maybe about some consistency results. So what happens as you get more and more data. You can actually derive closed forms, and I'm actually very excited to talk about this because this paper that derived closed forms for a certain subclass of rule of 3 posteriors, that's only a week old. And so that's very fresh off the press, even though, well, I should say fresh off archive. And the last point, if I get to it, is a duality form that we've been working on. So we've looked at the dual problem of that optimization problem. And it turns out that also has a very interesting interpretation. Okay, so let's start with the basics. Let's start with the Bayesian inference and Bayes rule. And if you know anything about Bayes rule, you probably know this phase. What you may not know, even though I think at this point it might actually already be fairly well known, is that this character that people like to depict when they talk about Bayesian inference is not actually the Reverend Thomas Bayes. And the other thing you might not know is that the formula that you all associate with Bayes rule actually doesn't occur in that form at all in the original paper by Thomas Bayes, but it appears in Laplace's follow-up paper roughly a decade later. And I wager that if Bayesian inference hadn't grown so popular in the 50s and 60s in the UK in particular, maybe we'd be calling it Laplacian inference, but that's maybe for another day. Okay, so Bayes rule, how do we use it in Bayesian inference? In Bayesian inference, the setup is that we have some observations, let's say n, and we have a prior belief about a parameter theta. And this parameter theta indexes a likelihood model, which is depicted in orange here. So your likelihood model is basically just, it's a probability model for the observations you have, and it depends on an unknown or a latent parameter theta. And what you do when you apply Bayes rule is you multiply your prior and your likelihood terms together, and you renormalize them, and you get your posterior belief. And operationally speaking, the interpretation of doing inference in this way is as belief updates. So you start with a prior belief, you observe your data, and then you have your posterior belief. So it's an update rule. And that's often how Bayesian inference is presented because it's very elegant and very intuitive. But actually, when you do this, you sort of make a couple of assumptions that people talk about less frequently. The first of which is that...
Jeremiah has to interrupt. I think Terry has a question.
Oh yeah, absolutely. Sorry, I didn't hear it.
Yeah, sorry. Thank you very much for this very clear introduction. So I was just going, I grumble a lot about Bayesian approach, largely because I'm skeptical about likelihood functions in high dimensions. But the question I was going to ask you is actually, probably just going to say this, but one of the prime assumptions I think that was wrong in what you just said, not that you're wrong, I mean it just is unreasonable, is that all of the measures in your family are absolutely continuous with respect to a specific measure. This is just not what happens in infinite dimensions. So let me give you an example. You know, you have an interacting cloud of atoms, say, then even the smallest change to the interactions between them will lead to a measure that's not absolutely continuous with respect to the starting one. And actually, I think a real issue about Bayesian approach is it doesn't give you any measure of the robustness of your choices of prior and posterior. Anyway, I'd just be interested to have your thoughts as you were saying it so nicely and so fundamentally. And I'll shut up because I'm not trying to have an argument about.
No, that's very interesting. I don't really think about infinite dimensional problems all that often, or at least not in the parametric sense. I don't usually think about infinite dimensional parameters that you do inference for. Yeah, I find myself. I was raised a frequentist and then got drawn into Bayesian inference far later. So I think I'm a bigger skeptic than most people that surround me. I do share your concerns with likelihoods, though I think my perspective on them is probably different. And I'll get to that later. I think likelihoods are problematic more in the applications of modern machine learning than in traditional sciences.
I think my objection to likelihoods is actually mainly to do with the maximum. I mean, and to do with whether the measures are absolutely continuous with respect to each other. But I think maximum likelihood is a useful artifact in some situations, but it doesn't have any intrinsic meaning.
I actually agree with that. I agree with that.
All right. Okay. Anyway, sorry.
No, that's very interesting. Right. So the assumptions that Terry just named are not on the slide. These are additional assumptions that can cause you problems. Today we'll be looking at slightly different concerns for the Bayesian posterior, because we won't really be focusing in on on absolute continuity requirements of the prior and posterior. But what we will look at are the requirements on the likelihoods. So my issue actually with likelihoods is this. In order for the probabilities you multiply together to have any sort of meaning, you actually need them to mean something. In other words, you need there to be a true theta star that accurately describes your data generating mechanism. And this is actually a fact that a lot of Bayesians like to gloss over, but that's actually a requirement that is needed. Otherwise, what does PB given A mean, right? Your probabilities, sure, you can multiply together probability functions, but they have no meaning for the real world. So you actually need this to hold true. The second thing you actually need to hold true in a strict, this comes from the decision theoretic underpinnings of Bayesian inference, is that your prior needs to encode all the information you have about the best possible value of theta. So you cannot just pick default priors, strictly speaking, in Bayesian inference, yet that is what most people do. It's curious how often your prior belief about a parameter ends up being a normal distribution, don't you think? So this is sort of two key points. And then the third key point actually has to do with computation. In Bayesian inference, the assumption is that when you have the posterior, you have everything you need. But that's not really the case in practice, because in order to work with that posterior, you need enough computational power to actually, for example, sample from it if you use a Markov chain Monte Carlo. And these three assumptions are sort of hidden in most of the methodology that statisticians derive for Bayesian inference. And I'll show you why that is on the next slide. The reason that the Bayesian posterior satisfies these, is based on these three assumptions, and that these three assumptions aren't usually considered a problem, has to do with the stylized thinking that we associate with the role of statistics in traditional sciences. And there, the idea is usually that you have a domain expert with some sort of data or problem, and this domain expert may or may not consult the statistician and then come up with some model. And this model will consist in the likelihood function and the prior. And then once you have those in place, both are assumed to be very well informed, because after all, they come from some domain expert who knows what he or she is talking about. And then really all you need to do is click the button, do inference, and the world has solved the problem. Now in machine learning, we actually approach things the other way around. People set up statistical models or algorithms, and then they throw them at problems. When you read any machine learning paper these days at NeurIPS or ICML, they will present an algorithm and then show you how it works on 10 data sets from the University of California, Irvine, I think, UCI data sets, right? They'll show you how it works on 10 of those data sets that they have just found somewhere on the internet in order to show you that the model can learn very complex problems. And so you see that the assumptions are actually at odds with how we do machine learning, because we do not actually observe the data or the problem first. We just propose a solution to a problem we haven't seen yet. And this is why the correct specification of a likelihood, the correct specification of a prior, actually can become a real problem. Okay, so just to summarize this last slide, or the last two slides, I should say, the first conclusion we draw is that the assumptions of Bayesian inference in traditional sciences, they're adequate, right? We can assume that correct likelihoods can be specified because we have the help of domain experts. We can assume that our priors encode at least some degree of the information available to us, because if you're a good scientist, then your experiments or studies should build on prior work. So it's already in the name, essentially. And in fact, there is an entire subfield in Bayesian statistics concerned with what's called prior elicitation, which is basically the question of how can you summarize prior findings into probability distributions. And the last point, which is the computation power, is not really a problem in traditional science, because if you set up an experiment, if you do drug testing for cancer research, let's say, then data collection is the bottleneck. That's the expensive part. The computational cost is not that important. But these things flip around in machine learning. Your correct likelihoods are basically, it's never possible to specify them because you've specified them before you even see the data. The priors often have no meaning. If you look at Bayesian neural networks, for example, you have highly parameterized differentiable functions, essentially, where nobody has really thought at all about what sort of weights in which layer, in which node are reasonable or not. And so any prior you impose upon a neural network are sort of artificial. They mean nothing. They don't necessarily encode any real information. And the third thing is that, and I think that's the least controversial of the three actually, is that in machine learning, virtually any application will violate the availability of near infinite computational power, which is why one of the main research directions in machine learning tends to be, or in Bayesian machine learning, I should say, tends to be the approximation of the Bayesian posterior by some means. Okay, so before I move on to the second part, maybe now is a good time to take some questions if there are any. Okay, I'll take that to mean that there are no questions, but if that's a misinterpretation, feel free to interrupt me at any time. So in the second part, what I want to do is I want you to stop thinking about Bayesian inference as some curves, like on the left-hand side, some distributions. I actually want you to think about Bayesian inference as an optimization problem, like we see on the right-hand side. And that will be the mission over the next few slides. So the first thing to note is that the Bayes posterior always solves an optimization problem. And this optimization problem actually is very intimately related to maximum likelihood estimation, like I think Terry was also pointing out earlier. And in particular, when you look at this equation, what you see is that you have essentially a regularized version of maximum likelihood estimation. And here the regularization happens by virtue of your prior belief. So let's go through this step by step. We have a space over which we perform the minimization. And that space is actually the space of all probability distributions on big theta, where big theta is the parameter space of your model. And what you're trying to minimize is an objective with two competing terms. The first term is the sum of negative log likelihoods. So this is a loss function, and it's the same loss function you would be minimizing in maximum likelihood estimate, and maximum likelihood estimation. And it's minimized at the maximum likelihood estimate, obviously. And the second term, which competes with that first term, is a divergence, and in particular the Kuiper-Gleiper divergence, which tells you how far you have deviated from your prior belief. So you're trying to balance your prior with what you actually see in practice in an additive way. And it's actually quite instructive, in my opinion, to think about Bayesian inference this way. I should say a divergence, in case you're not too familiar with these objects, there are pseudo-metrics on the spaces of probability measures in the sense that they are they're not distances because they're not symmetric. They do not satisfy the triangle inequality, but they are positive, or I should say non-negative, and they're zero if and only if both arguments are the same. And when you look at this problem, it's clear that you can now reinterpret inference rather than an update of a prior to a posterior. You can reinterpret it as a regularized form of loss minimization, where the loss in this case is the negative log likelihood. And this is actually quite nice because now we have three very different components in this optimization problem, and they just so happen to exactly address the issues that, or some of the issues we were discussing before. So let's start with the prior. Let's say you have a Bayesian neural network and you specify a prior belief. You already know that prior belief is not really a prior in the originally intended sense. So what you can do is you can actually replace the only component in this optimization problem that corresponds to the Bayesian posterior with a regularizer that is weaker. So in other words, you enforce your prior beliefs less strictly, right? So that would be one knob you can tune in this optimization problem. Another knob you can tune is actually the loss function. So if you don't like, for example, maximum likelihood estimation, or you don't think that probabilistic models are useful at all to describe the problem you're working with, you can replace this component, this middle component, this orange component, with any loss function of your choosing. So let's say you just care about the mean of the data. There's nothing stopping you from just plugging in the absolute difference between xi and theta here. So you could derive a posterior belief distribution about the median of your distribution. And this allows you to basically address the other concern we had, which is that the likelihood is probably misspecified. A special case of this that we'll look at later is actually using probabilistic models. So you continue using pxi given theta, but you're not scoring it with the negative log function. And the reason for that is that the negative log function is extremely sensitive to outliers. And you can actually see this if you look at the log function. You know what happens if log of x, when the x goes to 0 for log of x, the log goes crazy. And it basically, what this means for this problem is that if you have outliers in your data that cannot be well described by your parametric model, what happens is your posterior will try to basically inflate the variance to accommodate those few outliers. And we'll see later how this is actually a problem in some machine learning models, and replace the log with a robust scoring rule, which is derived from a robust divergence. In this case, the gamma divergence it will be. The third part, which is also the third problem we were discussing earlier, is the amount of computation power available to you. And you can reduce the computational budget you want to spend on solving this problem by minimizing it over a subspace of p theta. And in fact, this is already what people have done. You might be familiar with this equation because it's exactly what people usually refer to as the elbow, or evidence lower bound in machine learning. Only then they will have exchanged this p of theta here with some parametric family that is easier to optimize this objective over. Okay, and that basically settles the generalization we want to study, right? We have these three problems. We have an optimization problem with three components, which adequately addresses these problems. And so why don't we consider a broader class of problems where we replace the negative log likelihood with any loss function, we replace the Kuiper-Gleibel divergence with any other regularizer which is minimized at the prior, and we replace the space p theta with some subspace, or potentially subspace pi. And this object I'll refer to as the rule of three, and that's the optimization-centric generalization of Bayesian inference that I want to talk about. And in order to sort of abbreviate it, I will sometimes use this notation as well, where we just have the three components this problem depends upon summarized very concisely. Okay, why is this a useful generalization?
Can I just have another question before you move on? Sorry.
Yeah.
So you've got your log likelihood functions, and you're looking at essentially the stochastic process that adds them all up. And at least if you differentiate them, so they're score statistics, I suppose, then you remove the arbitrary constant. So then but then surely the assumption at that point is, well, not the assumption, if you were sampling from a true parameter value, then you would have a martingale, right? That's the whole point of doing this. So she wouldn't, rather than looking at the minimum, doesn't it make more sense to compare the value with the quadratic variation of the martingale? I mean, the basic idea is that this thing should be small compared with the sum.
Mm-hmm.
And it always seemed to me that it makes far more sense to compare it in terms of the quadratic variation of the martingale, rather than, so it's a scale, not just the minimum. I would have thought any point theta for which this number is small is a reasonable candidate for being a true parameter value.
So I'm not sure I understand completely. So we're back to no, that's I'm interested in understanding this. So you're saying,
well, I say that rather than, I mean, the reason you look for the minimum is actually because at the minimum the gradient is zero.
mm-hmm.
And the reason zero is a sense, but I would have said it makes more sense to differentiate the interior and get essentially a one form on the parameter space. And then the assumption would be that under the true parameter value, this one form is a martingale as you add n. And so you can expect it to be a lot smaller. So it's really about what is zero. What does a zero gradient mean? And looking just for the point where the gradient is zero, which is maximum likelihood, doesn't seem to me to hang out very well. But on the other hand, looking at the places where this quantity is small relative to the quadratic variation of the process, Does seem to make sense. But anyway, look, I'm
Right.
distracted.
Yeah. Okay, I think if I understand you correctly, you would like to change the loss function in here from the log likelihood to something that also encodes the second
The
order.
score statistic, to the score statistic, basically.
Yeah.
But viewed as a function on the whole manifold, which is parameterized by the thetas.
Interesting.
But anyway, we could talk about that a long time later.
No, that's interesting. I'd be interested if there's some literature that already does something like that to have a look.
Only a 30-year-old paper.
Those are the good ones usually. Yeah, you'd be surprised at. I mean, this form is from the 70s, so I'm not reinventing the wheel again. Okay. Right. So let's continue. So we have this generalization, and the question is it useful? We'll see later it's actually useful when you apply it, but useful also means, does it recover things we've already studied that we already know? And indeed it does. And for example, this block of four families of probability distributions are very well studied. So let's start with the Gibbs posterior or Gibbs Bayes distributions, sometimes also called pseudo Bayes or generalized Bayes. You get these by simply replacing the loss function. So you can still use the Kovac-Leibler regularizer, and you can still optimize over the space of all probability measures, and then you get a distribution that looks like this. So now the exponential of minus your likelihood essentially becomes your new pseudo likelihood, and this is why they're sometimes called pseudo posteriors, because these the exponential of minus the loss function is now interpreted as a new likelihood. Which, by the way, is problematic in its own right, because if you integrate an arbitrary loss function if you integrate an arbitrary loss function when you exponentiate it over x, it need not integrate to 1. So it's not actually really a loss function. Sorry, it's not actually really a likelihood function. So actually the two things are distinct. So this is why I don't like the word pseudo posterior, because this is not a pseudo likelihood. It's just not a likelihood. It's just a loss function. Okay, so you can change the loss function only. Now, obviously, if you change the loss function to minus the log likelihood and you plug that in here, the log of the exponential, they cancel and you're back to square one. And that's probably the most well-known problem here. That's the standard Bayesian problem. If you restrict attention to a subset, pi, which is parameterized by, let's say, kappa, so this is a variational family, as they call it in machine learning, then you get standard variational inference back. Of course, you can also get variational inference in the Gibbs Bayesian case. So if you're interested in a distribution like this, but you only optimize over subspace, you obtain what's sometimes called Gibbs variational inference. And the two new entries to this table that our work provides is basically looking at changing the regularization term as well. So people have looked at the idea of changing the loss before, but we thought, well, you really have three components here that seem to describe three different functions of the problem. Let's really look at all three of those jointly, and that is basically the inferential tool that came out of this work, which we call generalized variational inference. And the reason that you basically always needed this to be a variational inference problem is that this problem does not have a closed form in general if you replace the Kovac-Leibler divergence with another divergence D. Okay, so these are some special cases of interest. I'm sure I've missed a lot because this class of problems has been studied extensively. Okay, so just to sort out some terminology so we don't confuse ourselves, when I say the rule of three, I mean the mathematical generalization. And when I say generalized variational inference, I mean the inference procedure. So the idea of actually applying that generalization to data. And from what we saw earlier, we would expect that our generalization performs well on real data in various settings. And so, for example, two hypotheses that we formulated throughout the talk is that because priors on neural networks are basically ill-posed, they have no real meaning as a Bayesian prior, it means that if we make the regularizer weaker, then our inference should improve. And the other thing is that Gaussian likelihoods are basically inadequate for most real-world data sets, and yet they're sort of used as the default choice in many machine learning algorithms, one of which is the deep Gaussian process regression case. And so what I'll do now is just look at these two problems, not in great detail, but I'll just show you what happens if you actually make the regularizer weaker, or if you change the scoring rule from the negative log likelihood to a robust scoring rule. And what you find is that you actually get drastic improvements in both cases. So let's start with Bayesian neural networks. You can ignore the green results here. They're not important for what we're discussing today. What I want you to fix on first is the orange dot. The orange dot is always the baseline, because this is the standard variational inference case. So you're considering, again, the negative log likelihood, and you're considering the Kullback-Leibler divergence as the regularizer. And what we're doing here is we're just varying the prior regularizer, and we're making it weaker. The further up you go from orange, the blue dots all mark weaker regularizers above the variational inference case. This one blue dot over here, that's a stronger regularizer, and you can actually see we're doing worse for this case. And in all the examples, you see that if you make your prior regularizer weaker, in other words, if you give more weight to the data relative to the prior belief you've had, you actually get better outcomes. And these are negative test log likelihoods, so they're obtained on a test set. And similarly, the bottom, these are test root mean squared errors. So simply put, what this tells you is, it tells you two things actually. It tells you it pays to downweight your prior, but it also tells you there is some merit in using a regularizer in form of prior, because if you make the regularizer too weak, so you can see this, for example, in the Boston or the concrete data set, you can see this banana shape. The blue dots start bending backwards. And so that means you're improving performance by weakening the prior up to a point, and then you actually make it worse again. So there's still, if you're Bayesian, there's still reason to be hopeful, because you can only benefit so much from downweighting your prior belief. And the other thing we did is we looked at a machine learning algorithm which is called a deep Gaussian process regression. And all we did is changed the scoring rule from the negative log likelihood to the gamma divergence scoring rule, which is, there's a robust divergence which basically ensures that that outliers don't feature so heavily, and you get drastic improvements. So here the L, that's the number of layers in this deep model. The larger L is, the more complex this model becomes. And what you see is that for the vanilla case, where you use the negative log likelihood, you don't actually get a whole lot of improvement beyond 2 layers. And in some of the data sets, you don't get any improvement whatsoever. But if you change the scoring rule and you actually make it a robust scoring rule, in quite some of the data sets, here, for example, 1 layer already gives you a better performance than you get with 3 layers in the standard case. And even better, if you increase the number of layers for this robust scoring rule, you actually get better and better performances. So the picture this paints is that you actually get drastic performance increases from making your loss function a different one from the standard log likelihood. Okay, so the last part, like I said, is going to be a bit disparate. So it's going to be looking at different themes that have emerged in studying this problem. Some of them contributions that I've made, others that other people have looked at, and more looking at things that are less connected than what we've looked at so far. So again, at this point, I think it's a good place to pause quickly and ask if there are any questions about what I've presented so far.
Yes, I had the question. I don't know what you mean by weaker regularizer.
Oh, okay. So yeah, that's a good question. So the Kullback-Leibler divergence is actually relatively, it regularizes relatively strictly. So in the sense that if you have, even if you have the same mean, but your variances, let's say you have 2 normal distributions with the same mean, but your variances drift apart, then the Kullback-Leibler divergence will penalize that more and more and more, basically, I think, in a quadratic sense. So the further the variances are apart, even with the same mean, the Kullback-Leibler divergence grows in a quadratic sense. And other regularizers, for example, I think the Fisher divergence, as your variances drift apart, it grows to an asymptote, so it's bounded. So once the mean is fixed, there's only so much that the variance, the difference in variance, can increase the regularization value, if that makes sense.
Yeah, so the Fisher would be weaker or stronger than KL?
It would depend on the family of distributions you're optimizing over. If you want families that are always weaker, you can choose the alpha divergence or the Renyi alpha divergence. So here we looked at the Renyi alpha divergence, and a particular parameterization of that, which is such that if alpha exceeds 1, the regularizer is weaker, and if alpha is smaller than 1, the regularizer is strictly stronger than the KL. So this holds for all distributions in that case. So if you fix a prior, you basically have that, whiteboard would be really good right now. You basically have that the Renyi alpha divergence between Q and your prior always exceeds the Kullback-Leibler divergence between Q and your prior if alpha is smaller than 1. And conversely, if alpha is larger than 1, that inequality is flipped.
Yeah, thank you.
No worries. And the same is true for the alpha divergence. So actually, it's alpha is smaller than Renyi alpha is smaller than Kullback-Leibler for alpha larger 1, and the reverse is true for alpha smaller 1. So it's KL smaller than the Renyi alpha smaller than the alpha divergence. These are some that I'm aware of, but I'm sure there are other cases where the Kullback-Leibler is strictly larger than other excuse me, and other divergences. The Pinsker's result would be an example of that as well, though I don't recommend using the total variation distance as a regularizer. Any other questions?
Yeah, sorry, another question. So are there rules that tell you which one of these combinations of this triple are adapted to the specific problem that you are solving? So basically going back to the old statistician view.
Yeah, good question. So that's something actually I'm trying to work on at the moment. The other week, Pierre Alquier from Riken in Japan submitted a paper where he actually showed if you are in an online, you're doing what's this called again? Yeah, you're in an online setting and you know that your loss functions are unbounded. You basically get no regret bounds with the Kullback-Leibler divergence. But if you make your divergence stronger, in that case, you need to be stronger rather than weaker. If you make your divergence stronger, and in this case, he studied the chi-square divergence, you actually still get performance guarantees in the form of regret bounds. And these regret bounds grow at the same rate as the usual results in the literature. So people are starting to look into this stuff, but this is very young research. Like there's not a lot of this happening yet. The short answer to the question is, in general, no. We don't know which regularizer to use when yet, but we're starting to understand it a bit better. Okay. Right. So I'll move forward. Please feel free to interrupt me at any time. Also, questions that aren't related to what I'm currently speaking about. So there are lots of research directions on this. I came at this originally from an application focus. I was working on change point detection, and one of the problems you have with that, if you want to do online change point detection. So change points, by the way, is that you're in a time series and suddenly the nature of the time series shifts dramatically. But the problem is time series are also full of outliers and weird patterns, and you want to ignore those, but still be able to filter out the interesting changes that occur. And likelihood functions aren't actually very good at doing that. And so if you want to use a Bayesian framework, you actually need robust scoring rules. This is how I originally came at this problem. Then with the generalization, you've seen we looked at Bayesian neural networks and deep Gaussian processes, and there are many, many more applications, some of which I have not been involved with. And the second sort of part of this problem people have studied or beginning to study are statistical properties. So one can argue that the problem I've shown you earlier can actually be motivated from an axiomatic standpoint, and we'll get to that shortly. You can use it to reinterpret what variational inference actually is. You can study its frequentist consistency properties, which is sort of a tough nut, but quite some work has been done on this in the past 5 or 10 years. And like I said earlier, you can actually even study some of the regret bounds you get. So this is Pierre Alquier's work. In terms of the mathematical properties, so these are not properties connected to the data distribution at all. These are just sort of properties of the optimization problem itself. You can actually sometimes see what the optimizer looks like. So you get closed forms, and you can connect the problem to its dual, which is something I'm very excited about. So I'll speak about that very briefly in the end. Okay, so sorry. So for the axiomatic foundations of this problem, this is something we did a year ago or 2 years ago. You can basically set out a representation axiom, which tells you, based on the fact that we saw Bayesian inference was an optimization problem, we can basically say, well, any posterior belief we derive should look like an optimization problem with a similar form. And the form should be that you optimize over a space of probability measures, and it depends on the in-sample loss to be expected under your posterior and the deviation from the prior. And with that, you can basically show that any posterior belief distribution should be able to be written as an optimization problem like this. It's slightly tautological, but what's important here is that the relationship between the two arguments in F is not clear yet. So we know it depends on these two arguments, but we don't know how they interact with one another. And with some additional labor, basically by saying adding constants to the loss or adding constants to the divergence term shouldn't change your inference, which sort of makes sense. There's no information in constants. If you pose this axiom, and you restrict the attention to elementary operations, you can basically show that this is the form you should arrive at. Perhaps more interestingly, from a practical viewpoint, is that you can use this optimization-centric view on Bayesian inference to reinterpret what variational inference actually does. And if you're familiar with variational inference, what people usually think about is they think about a projection. They have the true holy grail Bayesian posterior, so that's denoted Q star B on the left-hand side, but they don't have the computation power to get it. So they want to minimize some form of distance, even though it's not really a distance, some pseudo distance into a parameterized set of distributions. Let's say the normals, for example. So here Q could be the normals, and your Bayesian posterior actually isn't normal. So you're trying to minimize the distance between the two, or the pseudo distance, and then take the point in the normals that minimizes that pseudo distance. And it actually turns out you can think about variational inference in this way as minimizing the Kullback-Leibler divergence between the true Bayesian posterior and the variational inference posterior. But the other thing is you can actually look at variational inference in what I think is a more intuitive way, which is as the constrained optimization version of the original Bayesian problem. We saw that this was the objective of Bayesian inference, and you solved it over all probability distributions. Now, if you just restrict attention to Q here, let's say the space of all normal distributions, you will look at the best possible value, the smallest value you can get inside the set of normal distributions. And so this is a difference of thinking about variational inference, which also produces different methods. So for example, in the projection-centric interpretation, what people have done frequently, so there's a lot of literature on this in the past 5 years, is they've said, well, if I'm minimizing this one pseudo distance, why don't I minimize some other pseudo distance? So for example, people have studied minimizing the chi-square distance between the true posterior and the set of normals, or the F divergences, and so forth and so forth. Whereas if you look at the optimization-centric view, it's much more appealing to actually change the objective directly. And actually, one thing this optimization-centric view also brings you is it tells you that if you have a fixed variational family, let's say pi, that you can compute your posterior in, and you really believe in the Bayesian objective that you posed at the beginning. Since you believe in the Bayesian posterior, presumably you believe in the objective that the Bayesian posterior is optimizing. So if you really believe in that objective, you can actually never do better inside this parametric family pi than the variational inference posterior, by definition, because it's the constrained, it's the pi constrained version of the original problem. And that also tells you immediately that any alternative method that operates in the same subspace pi can never be as good as the variational inference problem relative to the original objective. Okay, a third sort of chapter that people have looked at for this class of problems are consistency results. So what happens as n goes to infinity? And we sort of know under mild regularity conditions on, in the standard Bayesian case, we know that, so that's to say when you optimize over a space of all distributions, you regularize it as the Kullback-Leibler, and the loss is a correctly specified likelihood, even though it can be misspecified to some degree, and the following still holds. Then you get frequentist consistency, which means that your posterior actually concentrates to the minimizer of the expected loss. And you get the Bernstein-von Mises theorem, which tells you something about the speed of that convergence. And speed of that convergence happens at root n, which is to say your rescaled posterior is basically a normal distribution. And the question is, can these findings, which sort of are essential, can they be extended to these general forms? And if you vary only the loss function, there's quite a lot of work on studying the asymptotic behavior there. I'm currently involved in a study like that myself. And it basically so happens that if your loss is smooth and it has nice enough Taylor expansions, basically you get everything for free. If you're interested in this, I really recommend you read Jeffrey Miller's paper from 2019. He studies this very in depth. It's very nice to read. And it's probably the most general result of this form we have. If you vary only the space over which you optimize, then again, you basically need the likelihood function to be nice and the variational family to be large enough. So if the variational family doesn't contain the normals, obviously you won't be asymptotically normal. This was studied by a couple of people. Sorry, I don't have the references here. This is due to Yixin Wang primarily and David Bly. They had a paper at JASA in 2018. And that showed this. It's just called frequentist consistency of variational inference. And they use gamma convergence, which was actually introduced by other people before. So if you read the CM Journal of Uncertainty Quantification, you might be familiar with this type of problem. Usually it's called Bayesian inverse problem in that case. And they showed that this also holds if your pi is large enough. If you vary both pi and the loss, then basically the conditions that apply in the first case need to hold, and the conditions that apply in the second case need to hold. And again, you get a consistency in Bernstein-von Mises theorem. But all these results don't change the divergence. And the reason they don't do this is because you actually get closed form solutions whenever the divergence is the Kullback-Leibler divergence. And that's because it essentially makes everything log additive. Everything is additive on the log scale, and so you get a closed form solution, which we now know as the Bayesian posterior. What I tried to do is actually vary all three components and see what we get then. And this is a lot of work. Nobody's really looked at this class of problems before, so it was very difficult to even find the mathematical tools necessary to do this. In the end, it ended up being gamma convergence. I've managed to show that you get consistency. My suspicion is that you can show a Bernstein-von Mises theorem as well, but I haven't shown this yet. It's an open problem. So if you're interested in gamma convergence, this problem is still open. I'm happy to chat to you. Maybe we can figure it out together. Closed forms. The closed forms that we know are actually only the Gibbs posterior and the Bayesian posterior. And it was sort of unknown what happens if one changes the divergence. That is until last week, when Pierre Alquier published an archive preprint, which basically shows the closed forms under mild regularity conditions. using the Fenchel dual on phi divergences, which you might also know as F divergences. And the closed form here is equation 3.4, which probably doesn't mean a lot to you, or it doesn't look like a lot. So let's look at two special cases of this to sort of understand what's changing. So for example, if you use the chi-square divergence, which is a stronger regularizer than the Kovac-Leibniz divergence, you get this posterior, which tells you that before the loss was exponentially additive, and now it's just additive. So in other words, the regularizer is stronger here, much stronger, and you can see this in the posterior form itself. And similarly, if you have a p-power divergence, which is sort of the generalization of the chi-square divergence, you get a similar result where you downweight the loss terms even further. Okay, and then another thing that just happened a few weeks ago actually is that a collaborator of mine and I, we looked at the dual problem that you get when you study the dual of the optimization-centric generalization. And you can actually, it's a fantastic finding, you can rewrite it as an adversarial game, where the adversary basically tries to push you away from the loss you actually want to minimize. So let's say you want to minimize the loss L here. The adversary is trying to find the worst possible loss that it can push upon you, but it gets penalized as well for pushing away from L. And the way in which it's penalized from pushing away from L will be in this delta function here, which depends on your regularizer. And the first term is basically the what you're trying to solve. So you're trying to find an ethemum over this function h, but the adversary tries to push you away from L. So you are solving a function h that the adversary wants you to be as far away from L as possible. I'm not sure I explained that well, but the paper is coming soon, so you can read all about this hopefully in a few weeks' time. And yeah, with that, I think I also want to come to an end. So in summary, Bayesian inference is just one optimization problem with strict assumptions attached to it, which are often violated in machine learning. And there are many other optimization problems you could consider instead, though we don't know a lot about them yet. But we know enough already, basically, to know that often it might be better to solve an alternative problem than the Bayesian inference problem. And also, and perhaps even more importantly, if you find this set of questions interesting, then now is a really good time to get involved in this, because the study of these alternative problems has really just taken off now. It's a good time to get involved. And if you want to collaborate or talk about or chat about these problems, please get in touch. I'm always open to collaborate with people. I have enough open problems if you don't have any of your own. This is a very fascinating subject at the moment to follow. You can probably tell from the last few slides, a lot of this is happening right now. So it's moving quite quickly. But anyways, that's enough sales pitching, what I've been working on. Here's some references. And if you want to stay in touch with what I've been doing, you can just write me an email. I'm always happy to answer. You'll find most of the papers that I talked about today on my personal website. And if you like Twitter, you can follow me there. I sometimes give my 2 cents. All right. I think I stayed in time, and we still have some time for questions, I assume.